Hi friends, welcome to my channel, and today we are going to talk about certain solved questions which were asked in certain competitive exams. Today specifically I will be talking about those questions which was asked or which were asked in exam conducted by ISRO in the year 2018. There are a lot of questions to be addressed, so every video I will be trying to address 5 to 6 questions, and then I will explain the necessary theory also, so that it will be useful for the aspiring candidates. So this is a new series. I hope all of you will enjoy it, and without much ado, let's get started. Let's get started with a fairly simple question. So the question goes like this: material that exhibits the same elastic properties in all directions at a point is called. A fairly simple question. This is one assumption which we make before we try solving any particular problem. Let it be bending of beams or let it be buckling. We make this assumption throughout the study of solid mechanics. So that assumption is actually the material exhibits the same property in all directions. So that is this particular assumption. We assume that the material is isotropic. The correct answer is option C. Now regarding this question, let me tell you a few other things. uh, for a general isotropic material, normally there are 81 constants, and then we will bring the number of constants step by step. By invoking stress symmetry, we will bring it to 54. Then by invoking strain symmetry, we will further bring it down to 36. Then for hyperelastic materials, because of the existence of the strain energy function, you can bring down the number of constants further down to 21, in fact. Then with now we will start talking about special materials, like materials which are having planes of symmetry. For example, let's say monoclinic material where there is one plane of symmetry. Then you can further bring down the number of constants from 21 to 13. Then for orthotropic materials which are widely used in composites, or this particular material model suits the properties of composites. For orthotropic materials, what happens is you have three planes of symmetry, and these three planes are mutually perpendicular. Then you are left with 9 constants to deal with. Finally, not finally, even you can further say that your material is transversely isotropic. Then you are bringing down your number of constants to something like 5. Then finally, when you say the material exhibits the same properties in all directions, then you will say you just need two constants to characterize the behavior of the material. For an isotropic material, the two material constants can be either your Young's modulus and Poisson's ratio, or your Young's modulus and the shear modulus. So all these are different constants, material constants, which are used to describe the material behavior. I described all these things for your benefit only, because next time they may not ask the same question, but they can ask you a question from on similar lines. So that's why I thought of sharing those information with you. Now we have our second problem, which is fairly straightforward. Number of atoms per unit cell of face-centered cubic lattice is. Some people love to mug up things, but let's understand what is face-centered cubic in the first place. So you know there are atoms situated at the 8 corners of the unit cell, and then at the center of each face there will be a set of atoms, all right. As a single atom will be there at the center of each face. If you don't remember also, you can easily compute the number of atoms per unit cell without much difficulty. See, on the corner there are 8 atoms, right? And each of this 8 atom is shared by 8 unit cells. So the contribution of one particular atom to one unit cell will be 1 by 8. And we have 8 number of, or we have in fact 8 corners and 8 atoms occupying each of those corners. So that is the contribution from the atoms which are occupying the corners like this. Now in addition to this, there are we have atoms at the face center also. So there are altogether 6 faces, and on each face we have a atom situating. So what will be the contribution of one atom to one unit cell? Actually one atom is shared by 2 unit cells. Again that comes from logic. You arrange two cube, like two Rubik's cubes, one to one, then you will get to know, like face centered atom will be shared between only 2 unit cells. So the contribution is actually 1/2. So you can add this quantity and this quantity, so the number of atoms per unit cell of face centered cubic will be 4. So C is the right answer. Moving to the next question. See, before I move to the next question, even though you don't remember these numbers, try to bring in your logic and get the answer rather than just saying, "Oh, I forgot the value. Now I can't. I don't remember what is the number of atoms per unit cell and all those things." Try to use your logic and get the answer. Okay, even if you don't remember the exact value. Okay, now moving to the next question. Impact strength of the material is an index of its. So we know there are different types of impact tests, but the widely known impact tests are Charpy test and ISO test. So there is an index to fatigue strength. No, it is not an index to fatigue strength. Tensile strength, you may be having a doubt, so hold it. Then need not, and never it's a index of hardness. Okay, so you can rule out these two things and we are left with these two options. Actually the answer is toughness, because what happens in an impact test, you have a specimen and you are breaking it. The definition of toughness goes like this: the amount of energy it can store up to rupture. Okay, that is what is known as toughness. Now related to this problem, there are couple of things I want to convey. Actually hardness and the tensile strength of material is closely related. Okay, so that is why there are empirical formulae which will relate your hardness value to your strength of the material. That's why hardness tests are very popular, because they act as a very quick measure to evaluate the strength of the material. Okay, so there are correlations which connects the hardness and tensile strength, but the answer to this question is toughness. The second point I want to convey regarding this question is the difference between modulus of resilience and toughness. There was a gate problem I remember, in which they asked the difference between modulus of resilience and modulus of toughness. So resilience is the amount of energy absorbed until its linear elastic limit, or until its elastic limit. Okay, the material behaves elastically until this point, linear elastic till this point. After then it shows all kind of non-linearities. And also modulus of resilience is the area under the stress strain curve up to the linear limit. Now when you talk about toughness is slightly different. See, modulus of toughness is the area under the curve till fracture. Makes sense, because in an ISOD or Charpy test, you are not bending your ISOD or Charpy specimen to the linear elastic limit. You are breaking it. So actually you are going to the point of rupture. That's why this impact strength is a index of the toughness of the material. Makes sense? I think that clearly explains all these things. Now move to the fourth question. Fourth question is again pretty straightforward. In a sheet metal of 3 mm thickness, a hole of 7 mm diameter needs to be punched. The yield strength in tension of the sheet material is 120 MPa. The yield strength of the tension is 120 and the ultimate shear strength is 100 MPa. The force required to punch the hole. This is again, this type of question is seen very regularly. So apologies for my poor drawing. Let's say this is our plate and this is my punch. Now when I drill a hole, what I'm doing actually, I'm trying to do is I'm trying to remove a slice of material like this as shown over here. So actually I'm shearing this particular area. Clear? Okay, so what if, like, this is the circular piece. Actually my drawing is not that good. So this is the circular piece like this. Now this area I'm shearing. Okay, So this area will be perimeter times the thickness will give me this area. Make sense? So that will give me the area. Once area is known, what kind of failure mechanism it is there? It is actually getting sheared from the parent material. Makes sense? It is actually getting sheared. So you need to see what is the ultimate shear strength of the material. So ultimate shear strength times this area will give us the force required. So shear area is this much. I explained this already, like pi times the diameter. You have to be very careful while you're reading the problem, okay? Because if you make this mistake, like if accidentally you take the 7 mm as the radius of the hole, then your answer is wrong. So you are not just losing your marks, but you are also getting some negative marks also. So be always very careful when you solve this kind of simple problems in an objective exam. So the shear area is this much, then ultimate shear strength is given as 100 MPa. Now in order to evaluate the force, all you want to do is multiply ultimate shear strength with the shear area, which will give you the value 6.6 kilonewton. Okay, so here you can see option C is the right answer. Again, pretty straightforward. Now I will go to the last question that I'm planning to cover as part of this video. It's a very interesting question. My first suggestion is, especially when you're attending an exam like this where there is no preferential marking, like all the questions carry equal marks. So when you see this kind of problems which involves a lot of computation, kindly avoid this kind of problems and come back at a later time, because it will kill a lot of your time. Okay, so be careful with this. It's a very interesting problem. Pause the video, read the question on your own. So what they're trying to ask is, compute the reaction force acting at either P or Q when there is an increase in temperature by 10 degrees Celsius. There are a couple of points. The point number one, this is a statically indeterminate problem. Why it is an indeterminate problem? There are two reactions and we have only one reaction. One equation. Why there is only one equation? Because this is a one-dimensional problem. You just have the equation sigma fx is equal to 0. Then how to get away with that, or what is the solution? You need to remove the support, but once you remove the support, then you need to add a fictitious force like this. So now you are effectively replacing that particular constraint with a force, with some random force capital R. The direction is immaterial, like you don't have to worry too much about the direction. If in actual scenario, if R is acting like this, you will just get a negative value for R. So you don't have to bother too much about the sign convention, what I'm taking, all those stuff. Okay, now what you want to do? Let me detail out the procedure, or let me explain the procedure first in the first place. So this problem, there are two effects. One is the thermal effects. So due to this temperature raise by 10 degrees Celsius, this particular bar will elongate and this particular bar will elongate. That is effect number one. Next, now we have another force, external force, which is capital R. So this force will also try to elongate these two members. Okay, well and good. Now you can actually use the superposition principle and you can say the displacement seen at this location will be a summation of all these displacements. Make sense? Then what you will say, because you don't know R, now you need to incorporate your compatibility condition stating that displacement at this point should be 0. So that is the procedure. I will go step by step. You don't have to get scared if you didn't get a lot of things which I said. You don't have to worry. We'll go step by step. Let's say. So in the first place, let's consider thermal effects alone. Now if you consider thermal effects alone, this one moves by delta 1 and this one will move by delta 1 plus delta 2. Common sense, right? Because delta 2 is the relative elongation of second bar and delta 1 is the elongation of first bar itself. Okay, clear? Now let's move down. We know delta 1 is alpha, delta T, L, because these are arriving these are arising out of the thermal effects. So it is easily we can obtain delta 1 and delta 2. It's simply a plug and check, but always use consistent units. Don't put or don't substitute for L in meters, because the units of alpha was given in mm per mm. So all these things you have to be very careful when you are dealing with this kind of problems. Here also be always be careful with the units that you are working with. Okay, that's it. Now you consider all your thermal effects. Now what will be the displacement at this point due to this particular force capital R? Again, simple, not really difficult. You evaluate the relative displacement or the displacement of each of these bars separately, then add it. So you know this formula very well, I remember, because sorry, I guess you know this formula. This is a very simple or an elementary level formula, and you are computing what are the displacement because of this particular force capital R. Okay, so delta 1 will give you delta 1 R will give you the displacement at this point. Then delta 2 r will give you the displacement of this point with respect to this point. Okay, so the total displacement at this point due to capital R will be the summation of these two displacements. Again, common sense. Okay, nothing great. Now coming down, you know all the values. Now you bring your compatibility condition. You are saying, since there are two things in this problem, the displacement at that point will be a summation of all these things. These are arising out of the thermal effects, and these are arising out of the reaction. These are arising out of the reaction force which is acting at that point. Then, but when you add all these things together, you should get 0. Why? Because in the initial problem or in the original problem, that particular point is constrained. So that will leave us with this particular equation. The rest of the thing is simple plug and check, because you have applied all your concept till this point. So now you substitute for delta 1 under delta 2r like this, and you evaluate what will be the value of capital R. Very straightforward. No high fundamentals or nothing is required. But here again you have to be very careful regarding the units which you use. I generally work with megapascal, which is Newton per mm square, then Newton, then millimeter. So this is the consistent set of units that I work with. You can work with any set of units, but make sure they are consistent. Okay, so that's why you can see here I am substituting for 70 MPa, sorry, 70 GPa in 70 times 10 to the power 3 MPa. Okay, so you need to use always consistent units. Once you plug in all these numbers, then you will get the answer like this. So the answer will be 4060 Newton, and you can see a negative symbol here. That essentially means that my reaction force is acting in this direction. Nothing. This is simple thing. So don't worry about the minus symbol, why there is a minus symbol here, but the answer is 4060 Newton. So that is your answer. Thanks for watching. So I hope you understood the 5 problems that we discussed as part of this video. Thanks for watching. In the next video we will solve another set of 5 to 6 problems from these topics: material science, mechanics of solids and vibration, so that it will help you to prepare yourself for this kind of exams. Thanks for watching once again.